So for today, we are going to discuss Module 1 of CE 4241, Structural Engineering, which is the Introduction to Bridge Engineering. So when we talk about bridge, this is defined as a structure that would be built to span over physical obstacles such as bodies of water, valleys, and roads. So the main purpose of bridges is to provide passage over an obstacle and would be a key element in transportation system for three reasons. The first one is that bridge would control capacity and the cost per mile is expensive, and that if the bridge fails, the transportation system or the transportation network also fails. So as a key element of transportation, how do we see that it controls the capacity of transportation flow? So it controls capacity through volume and weight. And with that, if the bridge now has insufficient carriage width, it would probably, or it would not be able to carry out the flow that it is required to carry. So a small carriage flow would constrict now or carriage width would constrict our flow of traffic. So you analyze it as a bottle with, so yung tinatawag nating bottleneck. So the body of the bottle would be your highway or your road. And then the opening, which is much smaller or thinner compared to the body, would be our bridge. So if that bridge is smaller compared to that of the body, then there will now what we call a bottleneck or the start of a traffic jam. Okay? So also, it controls capacity through its strength deficiency. Meaning, if the bridge designed will not be able to carry the load that it is required to carry, so if not, it's not able to carry heavy loads such as trucks, then there would be some problems. So kung yung highway natin or yung route natin is a route that should be used by heavy vehicles, then the bridge that you have to design should be able to carry that load. Okay? So with that, the load limits will now cause rerouting of the traffic, which is again expensive in the way of planning and design. So kailangan natin maghanap ng other route na pwedeng dumaan yung mga heavy trucks natin. So if you are a frequent traveler and you usually pass through bridges, you would see now some signages wherein it gives us a heads up that the vehicles that could pass only through that bridge has a limit. So meron yung nakalagay na picture ng truck tapos nakalagay kung gaano lang kabigat yung pwedeng dumaan. So pag hindi pwede yung weight ng sasakyan doon sa bridge na yon, then you have to reroute your vehicle. Okay? So next, the bridge is expensive per mile because it is a major investment. Building bridges is much higher, much expensive compared to building highways or roads. Therefore, it should be planned carefully for the best use of funds for the project. It costs high compared to our roadways. And lastly, if the bridge fails, the transportation system fails. So whenever a bridge is removed or is not repaired or replaced right away, the transportation system would be restricted of its function. So pag hindi pwedeng gamitin yung bridge, anong mangyayari? You have to reroute. You have to look for a way. So it would be a hassle already it is a failure to the network or the traffic flow. So bridge now would be a structural system that would always be exposed to external forces. Therefore, there are major concerns with regards to its design. One is that it is always exposed to different kinds of temperature. Thus, we have your thermal effect. And then, with regards to its durability, because of its exposure to natural factors, you have to take note also of its strength. And lastly, cost. It is a major concern since there will always be inspection and maintenance of the bridge, just like our highways or roadways. It will always be subjected to large moving and repetitive loads. Therefore, fatigue also is a primary concern in our design. So it accumulates damage as over its design life or over its usage. So we have to take note also of the effect or kung gaano ba katagal yung design life niya. So we can be able to approximate kailan natin or estimate when the bridge has to be repaired or to be improved. So the fatigue would also result in cracking, and when there's cracking, there's a possibility of failure already. So the bridge engineering would be a field of engineering, specifically structural engineering, that would deal with surveying, plan, design, and analysis, construction management, and maintenance of bridges. As a bridge engineer, you must ensure that the design would satisfy the design standard, and you should be responsible to any structural safety and serviceability of the bridge. In bridge engineering, we have several civil engineering disciplines that would be involved in our design and plan. One is highway design, which would cover overpass and underpass alignment and the geometry of the bridge. Structural design for the superstructure and substructure elements. Geotechnical engineering, which would cover the design for pier and abutment foundations. Hydraulic engineering for proper bridge span length and drainage of bridge site, especially if it would be for bridges that is located over bodies of water. Then we have surveying and mapping, which is used for the layout and grading of our proposed site or proposed bridge project. So there are different classifications of bridges. So we classify them differently based on several factors. So the first one is classification of bridges based on its span length. And there are three span length or classes of bridge with regards to the length. The first one is the short span bridge, the medium span bridge, and the long span bridge. A special classification based on span length is what we call your culvert bridges. Another classification is based on the structural form or the superstructure of the bridge. So the first one is an arc bridge, a truss bridge, beam or a girder bridge, a slab bridge, a suspension bridge, and a cable-stayed bridge. Based on interspan, meaning how they are connected. The first is, or how is based on their support. So the first one is simply supported, continuous bridge, and a cantilever bridge. So based on deck location, so the deck would be that portion of the bridge where traffic will flow. So where is it located? Its classification now would be if it's called a deck bridge, a through bridge, or a half or a semi-through bridge. Another classification is based on the material used for the construction of the bridge. The first one is stone or masonry bridge, timber or wooden bridges, metal or steel bridge, RCC bridge or reinforced concrete bridge, and pre-stressed concrete bridge. Another classification would be based on the position, which is the bascule, a swing, or the leaf. Based on the purpose or the use of the bridge or the intent of use, then we have a highway bridge, a railroad bridge, a pedestrian bridge, a pipeline bridge, and others. This would also include your aqueducts. Next, we have based on geometry. Basically, this will now be based on the geometry of its abutment. So we have a straight bridge, a skewed bridge, and a curved bridge. So for the first classifications based on the span length, we have the short span bridge or a minor bridge. These are bridges whose end supports would span up to no more than 30 meters. These are slab bridges, pre-stressed concrete shapes, and steel shape bridges. Next, we have medium span bridge or a major bridge. So these are bridges that would have lengths of 30 meters up to 120 meters. So there are girder bridges or made up of pre-stressed and steel, usually will be for medium span bridge. Then for long span bridges, this would be bridges having spans between the supports of more than 120 meters. Examples of this would be cable-stayed and suspension bridges. So we could also use post-tension concrete and steel bridges, but we have to make sure that it is made up of high-strength materials. For culvert bridges, this would be bridges that would span from a length of 6 to 8 meters. Okay? So for short span, it's from 8 to 30 meters. Okay? So what is the difference between a bridge and a culvert? So when we say bridge, there is passage over an obstacle such as a body of water. While for culvert, it permits a body of water to pass under an obstacle such as a road. So bridge over an obstacle, culvert under an obstacle. So for bridge, it would provide passage of traffic flow, vehicle or pedestrian traffic, while for culvert, it would provide the benefit or passage of water. For a bridge, it would have a base over which traffic can pass, while culvert will have a base over which water flows. So this is the difference between a culvert and a bridge. So for a bridge, we have an obstacle, body of water. So it is built over the obstacle and it provides traffic flow. Ito culvert, it provides water flow. And most possibly, will have a roadway that would be built over here o kaya we have some structure that would be built near it so we avoid water flow passing through that structure. Okay? So next we have based on structure or based on the superstructure. So the first one is your arc bridge under structure. So this is a bridge with abutments at each end that is shaped as a curved arc. So through the curved arc, this would now transfer weight of the bridge and its load primarily into a horizontal truss that is restrained by the abutments at either ends or either side of the bridge. The arches would be the primary force that will resist elements or forces, and the arches would basically resist force through compression. The truss would be a major consideration for our design. So for an arc bridge, so Basically, the load will be distributed from this point and will be distributed to either to both ends of your bridge. Okay, so the load will be distributed to the abutment. Okay. Next, from there, action reaction, the abutment would now also squeeze through and push back the load from the ground. So the ground would now resist the load through the abutment. Okay? And then from there, the resisting force in the abutment would be distributed back along the arc toward the keystone. Yung keystone natin, itong nasa gitna, which supports the load. So basically, it's just simply a transfer of load and action reaction. Okay, so distribution of load towards the abutment. So from the abutment, it will be giving it back, or you will be giving it to the soil or the ground, and the ground will react through the abutment. Thus, we have compression on the bridge. So these are examples of arc bridges. So this is an arc bridge, a deck arc bridge. This is a viaduct, aqueduct. This is a tied arc bridge, corbel arc bridge, and a through arc bridge. So for some of these bridges, they would also fall onto different classifications of bridges, such as the through arc bridge, the deck arc, and the tied arc bridge. So next, we have the beam bridge. So from the name itself, it is made up of beam or a girder. So the weight on top of the beam would push straight down on the abutment at either end of the bridge, and the weight would be applied at either end of and then counteract bending at the center. So beam must be strong in both compression and tension so as to resist twisting and bending under heavy loads. So the usual span for a beam bridge is a maximum of 200 feet long. So we have here an example of a beam bridge. So we have two types of girder or beam bridges. First one is a pre-stressed concrete girder, a steel girder, wherein the girders would be, or your beams would be the primary force resisting the elements. Then the forces are resisted through bending. So this is an example of a beam bridge or a girder bridge. This is a slab on a stringer or a T-girder bridge, which would span 10 to 25 meters, or that's 33 to 82 feet. This one is a railroad steel girder bridge. Okay, so next we have a slab bridge. This would be the simplest type and the least expensive structure that can be used for small or minor bridges. And it's up to 12, usually up to 12 meters. So this is the Heinz land span deck slab bridge. So slab bridge lang siya. Wala masyadong support. Okay. Next, truss bridge. These are kept strong by the stiffness of the structure. So all beams or members work together in order to spread out the load carried by the bridge. So this is used for larger spans where the depth of the girder bridge is not practical due to the limitations of the following. We have fabrication, the erection or the building, transportation, and economy in case for concrete girders. The rods or the members would be the primary force resisting elements. Forces are resisted through tension and compression. So you already know from mechanics that for trusses, there will always be tension and compression present in the structure. So this is an example of truss bridges. So we have Buntun Bridge, which is found in Tuguegarao, which is the second longest bridge in the Philippines. We have the Q Railway Bridge, which is an example of a lattice-type truss bridge, which spans over River Thames in London, England. Then we have here a steel front truss over the French River. So there are different types of truss bridges based on what type of truss you used for the bridge. Okay. Next is suspension bridge, which would allow long spans for bridges. The bed of the bridge can be continuous and is held up by cables, which is stretched between the piers. So in a suspension bridge, the load-bearing portion would be hung below suspension cables on vertical suspenders. There are two types of suspension bridges or bridges that would use cables. We have the cable-stayed bridge, wherein the cables are rigid and are directly connected to the deck of bridge, and suspension bridge, which is hung vertically off another cable supported by the piers. So for a suspension bridge, if we are going to look at this diagram, so you can see that we have here the suspended cable or the cable, and we have the vertical cables which are supporting the bridge or connecting the cables or tension cables and the deck. And if we are going to look at the connection of the tension cables, it is connected to an anchorage and on the towers or pylons. So it's not connected directly on the bridge itself, but on an anchorage and a tower. So for a suspension bridge, cables would be the primary force resisting element, and the force are primarily transmitted or transferred through tension. Next is the cable-stayed bridge, which consists one or more columns, or we also call towers or pylons, with cables supporting the bridge deck. So there are two types of cable-stayed bridge. We have the heart design, in which the cables are made nearly parallel by attaching them to various points on the tower, and a fan design, wherein the cables would connect to or pass over the top of the tower. So this is now an example of a heart design. So as you can see, the cables would look like or more likely be parallel to each other. So it's connected at different positions or points in the tower as well as the bridge deck. So it's directly connected to the bridge deck, and there is no need for a anchorage point. So for a fan design, it looks like that they are connected at a certain or common point, but they are more likely not parallel with each other. So same as for harp design, the cables are directly connected to the bridge deck. Next, we have the classification of bridge based on interspan. So the first one is simply supported bridge, which are used when the width of gap is small and only single span of bridge is required. This is more suitable for short span or minor bridges. Next, we have continuous supported bridges, which is used when the width of gap is quite large and where there is no chance of an even settlement. So this is more for minor or for major bridges. Moments are generally developed at the pier supports, resulting to reduction of stress at the inner span. So here is an example of a simply supported bridge. So take note that it is usually for the short span bridges. So it's supported on the ends. We only have two supports, for the bridge, and we have a continuous supported bridge, wherein we have several supports in between the span or the entire length of the bridge. And then, the last one, we have the cantilever bridge, wherein we have two types. We have the simple cantilever, which is formed by two cantilever arms, which extends from opposite sides of the obstacle to be crossed. They would meet at the center of the bridge. And the next one is the balanced cantilever. So this would be cantilever spans, counterbalance each cantilever arm with another cantilever projecting the opposite direction. So here is a diagram of a simple cantilever bridge, wherein we have two cantilevers that is coming from both ends of the bridge and would meet up at the center. So there is now a connection between them, which is called a suspended, which is the suspended part of the bridge. So this part now is not a part of both cantilevers. So an example of a simple cantilever bridge is this bridge. So it's located on the east of Scotland and west of central Edinburgh. So this is the fourth bridge, which is a cantilever railway bridge. So here is an example of a balanced cantilever bridge. So as you can see, we have a single support here, and then one arm counteracts or counterbalance the other arm. So we could also have a series of balanced cantilevers or a series of cantilevers for a bridge, but as you can see, they are not connected by a suspended part. This is an example. So this is your cantilever arm, then this is another cantilever arm. So based on the deck location, we have what we call the deck bridge. So it simply means that the floor or the deck of the bridge is situated on top of the floor of the flange in case of plate girder bridges. So the floor is on the top chord in case of truss bridge, and the top bracing would not be required. Okay, so this is an example of a deck bridge. So as you can see, the deck is on the very top and it is where the traffic would flow. Nasa taas. So next we have through bridge, wherein the floor is placed at the level of the lower chord for truss type bridges, and in here the top chord is braced laterally. But to distinguish the difference between a deck bridge and a through bridge, basically a through bridge would have its flooring provided at the bottom of the superstructure, unlike the deck bridge wherein the deck is located above the superstructure or the superstructure itself. So an example of a through bridge is the Chao Tianmen bridge found in China. So it's below the superstructure bridge. We have the half-through type bridge or a semi-through type bridge, wherein the floor would lie between the top and the bottom chords. So for some, there are double-deck bridges constructed to carry both traffic for roadways and railways at the same time. So more specific definition of a half-through type bridge is that the flooring would be located at intermediate level of the superstructure or between the superstructure. So an example of that is the Bayonne Bridge in New York. So based on material, we have wood or timber bridges. So this, from the name itself, these are bridges made out of wood or timber. So it's basically used for short spans only and would not, and since it's made out of wood, it's not sufficient for heavy loading. So usually it's designed for pedestrians or low weight transport. For some timber bridges, they would allow pedestrian or bicycles. And then this is now an example of a timber bridge. Okay. Next, we have masonry bridge. So this is made out of bricks or stones, and it's more durable compared to timber bridges. Though it's also same as timber bridges, only suitable for shorter spans. So next we have the steel bridge, which uses steel bars or trusses or steel cables as its main construction material. So it's more durable and would bear heavy loads. Reinforced concrete bridge, this would be using RCC as its construction material and is more stable and durable compared to steel bridges. Suitable for long span and heavily loaded traffic and is generally used for constructing flyovers and highway bridges. Then lastly, we have the pre-stressed concrete bridge, which is suitable for long span bridges, has heavy load carrying capacity, and would require high tensile steel, which is more expensive than ordinary mild steel. So this is an example of a steel bridge, a reinforced concrete bridge, and this is a component used for a pre-stressed concrete bridge. So next we have based on the deck position, we have the movable bridge, which is designed to move out of the way of boats or other kinds of traffic. Okay. So it's powered by electric motors, whether operating winches, gearing, or hydraulic pistons. So we have three types. The first one is the bascule. So if you can see, it moves through one point. So pag tumaas yan, boats can already pass through the waterway. Okay. So next, we have the swing bridge. Swing meaning na para lang siyang nag-swing. So, umiikot lang siya. So, that's for a swing. And lastly, we have the lift. So, for the lift, so if we have a larger boat, then the bridge will be moving up so that larger boats would be able to pass through under the bridge or through the waterway. Okay. So next, we have based on the purpose or the use. So we have pedestrian bridges, or we also call this as footbridge, which from the name itself, it's designed for the use of pedestrians only. Some pedestrian bridges also is allows bicycles to pass through it. Okay? So an example of your footbridge or pedestrian bridge is that Stairway to Heaven found in EDSA. Railway bridges, this is used for the movement of trains. Usually, steel bridges is used for its construction. So we have here Padre Zamora Bridge found in Manila. Okay. So it's for the use of trains, pero ang gumagamit is yung trolley. We have highway bridges. So it's designed for the passage of vehicles, and for some, it allows also passage of pedestrian. So it's designed for heavy rolling, which is up to 0.8 mega newtons. So this is the San Juanico Bridge, the longest bridge in the Philippines. And then we have pipeline bridges, which is used for supporting pipeline on deck slab of bridges. So it's usually used for oil, gas, water, and communication lines. So this is an example of a pipeline bridge. Then we have your aqueducts or water bridges. So these are bridges constructed to convey water courses across gaps or spaces. So lastly, we have based on geometry. So we have the straight, the skew, and the curve. So a straight would have a support that's standing up straight. Skew, medyo naka-angle siya. And then yung curve, naka-curve siya. So the most advisable between the three bridges is the curve bridge. Take note that for bridges, we can classify them with the different classifications of different factors, such as this bridge that we have shown earlier. So we could classify this as a truss bridge, a steel bridge, a deck bridge, and a railroad bridge. So depending on the type of support, we could also define this or classify this based on its support. Okay, so that's for part 1 of module 1 of bridge engineering.